I'm Richard Hollingham. Welcome to our Best of 2012 Planet Earth podcast, a bumper edition featuring Hoff crabs, cave art, Olympics and shags, which condensed into 10 seconds sounds like this.
Oh, it's quite small, isn't it?
About a 4-metre Nile crocodile.
And then blowing or spitting pigment.
And they do have a tendency to fall over quite a lot.
We start with a brand new species, the Hoff crab. UK scientists discovered the animal along with many other new creatures during a research expedition along the East Scotia Ridge of the Southern Ocean. Named for its hairy chest, the Hoff crab lives in large numbers around volcanic vents. Sue Nelson went to see one of the crabs at the British Antarctic Survey in Cambridge, where she met geologist Ali Graham and first marine biologist Katrin Linzer.
So we open this little tub and take one of the specimens out.
Oh, it's quite small, isn't it? That could easily fit in the palm of my hand. They're white and pale, presumably because there's no light down there.
This is a small female. She's about 6 centimetres tall. The large males were up to 12 centimetres tall and they had big claws. But also the females, you can clearly see a really hairy chest and along the bottom of their legs.
So it's not just the males then that had the hairy chest, it's the
No,
females
the other
too.
females have it too.
Ali, tell me a little bit about where these creatures were found, because they're beside some very unusual structures called hydrothermal vents.
The East Scotia Ridge itself is an area where the seafloor, the lithosphere, which is the hard outer shell of the Earth, is actually extending and it's stretching. And where this happens, magma from the mantle actually upwells, and along the ridge itself you get volcanic activity. And because the crust has a lot of water in it, that water is heated geothermally like geysers in Iceland. And eventually through fissures and through fractures and faults in the crust, this hot water finds its way out, and it finds its way out through vents.
And these vents look almost like a sort of termite's nest, tall tapering structures but with these enormous plumes of smoke coming out, which I assume are sulphurous.
Exactly, it's a very good description. They are tall, conical sort of chimneys. The waters that come out of these vents are enriched with minerals which are extracted from the mantle. The chimney is formed of precipitates that come out of the water that's emerging from the ocean floor. The reason you get these black smokers is because you have these sulfides coming out and they precipitate straight out into the ocean and make this black, thick smoke.
How many new species did you discover?
Well, we're still counting them because we don't know. We do know we have so far 15 species that are clearly linked with the hydrothermal vents in the Antarctic, and none of these species have ever been found before. But in the land, we call it the vent periphery with diffuse warm flow, we found another 25 to 30 species that might be linked with the vents or might be Antarctic deep-sea species, and we need to check if these are new to science as well.
Katrin Linzer from the British Antarctic Survey. You'll see pictures of the Hoff crab on Planet Earth Online, where you'll also find all the podcasts from the past year. We're going to head somewhere considerably warmer now, Turkey, where a major international project is underway to investigate the North Anatolian Fault, the cause of the 1999 Izmit earthquake, which killed more than 17,000 people. Hannah Bentham from the University of Leeds joined a group of scientists installing seismometers in the area, some 3 hours' drive east of Istanbul. We join Hannah as the team is hard at work.
Just to introduce Dr. David Cornwell from the University of Leeds. And David, what are you doing here?
Well, I'm digging a hole about 1/2 metre deep. We're going to put the seismometer down at the bottom of the hole. We'll put some sand down first, level the bottom of the hole, and put a plate on top of it, normal floor tile, and then the seismometer will rest on top of that, and then we will backfill it with the earth.
We were a bit late getting to our first site of the day due to a bit of an accident with a hacksaw, a finger, which ended up in a visit to casualty. So we arrived a bit late and about midday, so we're in a really, really remote village in the middle of the mountains, and we are struggling to find somewhere for food. And so we spoke to some local farmers asking them where we could eat, and they brought us some bread, some spring onions and some strawberries. And so we thought that was it, and then they've invited us in for lunch. So I've stuck out to do a bit of a recording. I just wanted to express how amazing the hospitality is here. We are installing an instrument in this man's land, and they invite us in for lunch and bring out tea, biscuits, loads and loads of tomatoes, apples, cucumbers, the brightest tomatoes you've ever seen. And it's just amazing how warm these people are. I'm really, really touched today. Once the seismometer is in the ground and recording, one of the things we have to do is a stomp test. And what that consists of is 3 very large stomps on the ground, followed by a 1 large stomp. And what we have to do is to check that we see these stomps in the waveforms on the computer. So as you can hear in the background, stomps are going on. And just looking at the computer, we see the 3 components, the up, so the Z component, the north and the easterly components, and we can see that the stomp tests are coming in now. Yes, we see 1, 2, 3 wiggles and then followed by 1. Brilliant. So the seismometer is working well. We're just packing up the car and going to leave the site, and therefore we're done for the whole day. Currently we've deployed 62 of the instruments, so another 4 need to be done tomorrow. And say it's been a really good day. We met some fantastic people, seen some beautiful sights, and done some good science.
An extract from Hannah Bentham's audio diary recorded in Turkey. In the run-up to the London Olympics, one of the big concerns was air pollution. After all, air quality in London regularly fails to meet European standards. Ahead of the Olympics, I visited the University of Leicester, where scientists, led by Roland Lee, have developed a new scanner system.
So our urban environments are cleaner than they used to be, but still we have a lot of emissions that come from the traffic network in particular. We have nitrogen dioxide, we have particulate matter, and we have ozone coming out of the exhaust of cars that then we breathe in.
And what's that doing to us?
Some of it affects the airways to the lungs, so what we breathe in and our respiratory tract and the way that our body responds to that, and some of it gets into our bloodstream and actually affects the cardiovascular system and how our heart responds.
So none of that's good. Where's it all coming from?
Much of it, 95% of the nitrogen dioxide, for example, in an urban environment, comes from the vehicles, from cars, from heavy goods vehicles, and from buses.
Now, pollution is already monitored. There are monitoring stations around the country, particularly in big cities. But you've developed a new type of scanner, which is here in front of us. Now, I guess it looks a bit like an oversized speed camera. Or, if you're into your television history, one of the original BBC TV cameras from the 1930s, mounted on a plinth. So that means it can rotate. It's triangular, I suppose, with a hatch at one side.
We realised several years ago that we could monitor air quality using scattered sunlight. So there is a possibility to create an instrument that just receives scattered sunlight and tells you how much nitrogen dioxide there is in the air. So this instrument is designed to sit on top of a tall building and produce an image of the nitrogen dioxide over a complete urban environment, really letting you see the individual emission sources and where those pollutants end up downwind.
So does that mean you can map where these particular pollutants are, where these chemicals are in the atmosphere, rather than get a snapshot of how much there is?
Exactly, yes. Yes, with multiple instruments you can get a 3D reconstruction of where these gas fields are. So traditional sensors take in a single point measurement. They suck in air down a tube and they give you a very accurate point measurement that might be by a roadside. We, between 2 or 3 instruments, can map out a complete urban area and tell you where the nitrogen dioxide is in that space.
It is a curious-looking machine. It's, imagine around the size of a microwave oven, but a triangular microwave oven. And you look inside, it's full of circuit boards and wires. And there's a box in the middle which is covered in a silver bubble wrap. I guess that's the heart of it.
Exactly, that's the heart of the instrument. That's a spectrometer that was originally designed to be a satellite instrument for air quality mapping by Surrey Satellite Technologies. We built the first one of these spectrometers ever to be made in the world. It produces very, very nice data for exactly what we're needing here, which is air quality information in our scattered sunlight data. So we have one of those spectrometers sat in the middle of a rotating turret, collecting sunlight and mapping out the air quality.
This scanner isn't the only application of equipment originally developed for space. Down the road in the emergency department at the Leicester Royal Infirmary, environmental sensor technology is being adapted for medical diagnostics. The idea is to apply the techniques used to analyse air to analyse breath. Paul Monks hooked me up to one of the instruments they're using.
What we've got just in front of us is a series of breath sampling units, and what we use that for is regularising the amount of breath. And what we're going to do is we're going to set you a target to breathe to and get you to what's called tidal breathing, which is gentle breathing in and out. Then we'll take the air and we'll put it into our mass spectrometer, we'll add some water to it, and we'll actually take some fingerprints. So chemical fingerprints of your breath, and then we'll weigh the molecules in there, and we'll check whether, for instance, you're a smoker.
I'm not a smoker.
Or whether you've got diabetes. They're very easy things to see virtually instantaneously on the screen.
Okay, well, let's give it a go. So this is the mouthpiece. It looks, I suppose, like an asthma inhaler attached to a bit of piping with a long lead going off into the machine. So I've got to breathe in time to the beeping. Okay.
You should be so kind.
What you can see on the screen now as you're doing this is actually the CO2 in your breath, which is what we use as a marker in order to do that. And then on the top is the volume of air that you're putting out into our instrument. And what we're trying to do is get you here to regularise your breathing so we can get the same amount of air into the instrument. And we can see on the mass spectrometer screen behind us the chemical data coming up from the measurements that we're making.
I must say I was pretty rubbish at breathing in time with a beep. That was quite difficult.
Well, actually, your breathing's quite regular, though your volume's a bit all over the place.
Oh, okay, yes. Yeah.
So now as we move over...
So we move over to
the
mass spectrometer, which is this shiny collection of tubes, and here's the screen with my breath analysed.
Yes, so we're actually looking at the chemicals in your breath, and we've looked at it in real time. And that was one of the real innovations of the work that we're doing, is that you can actually measure atmospheric composition, but also breath in real time. And what we've got up on the screen here are peaks like acetone, which is a diabetic marker. Also ethanol, just to check that you haven't had a drink this afternoon before you came to join us. And no, you've actually got a flat baseline of ethanol there, so you're looking quite good.
So is that okay?
Yes, you'll live.
And for a hospital environment, this is a fairly fearsome bit of equipment. I imagine it's also very expensive. You really need to miniaturise this, don't you?
Yeah, to use the words of Star Trek, we're boldly going where no person has been before. And that's the discovery phase. So actually you need big instruments with a lot of functionality in order to explore the human breath. The idea at the end of the day is actually to miniaturise these things and maybe even produce handheld diagnostics. Something like the size of a glasses case that you'll be able to breathe into. Maybe even one day your mobile phone.
Paul Monks from the University of Leicester. This is the Planet Earth podcast featuring some of our highlights from 2012. To listen again to any of the 24 podcasts we've made in the last year, do visit Planet Earth Online, where you'll find all the audio and descriptions. You can also follow us on Facebook and Twitter. To reach us, just search for Planet Earth Online. Back 50,000 years ago now to the final days of the Neanderthals and the rise of modern man. Research published this year in the journal Science has revealed the oldest known cave art in Europe, and it might not have been painted by humans. I went to the University of Bristol to talk to the archaeologist who led the project, Alistair Pike, and as they didn't have a cave handy, Alistair projected the art onto a wall of the Lecture Theatre.
We're looking at the Panel of Hands. It's a part of a cave called El Castillo Cave in northern Spain, very close to Santander. And this part of the cave, maybe 41,000 years ago, was decorated by people putting their hands against the cave wall and then blowing or spitting pigment to create these negative hand images.
How old are these?
Next to the handprints there are some red dots, and one of those red dots is at least 40,800. But because we can see that they were made in the same technique, they don't overlay each other, we think actually the handprints were made at the same time.
What does that mean then? I mean, it sounds an awful long time ago, but that has particular significance.
Yes, well, first of all, it's at least 15,000 years older than we previously thought the art in this cave to be. But it dates from around the time when modern humans first arrived in Europe and the Neanderthals begin to disappear. But because we're dating these deposits on top of the art, we don't actually know how old the art is. All we know is it's older than 40,800, and therefore it might have been made by Neanderthals.
Would that be their first?
Absolutely, or certainly painting. This would be the first example of Neanderthal painting. So you can look at the fingers, the handprints of Neanderthals, if indeed this is the case. But we do know that Neanderthals, maybe 50,000 years ago, were making art-like objects in other parts of Spain. So we find things like shell beads to use for body adornment. We find shells that have traces of pigment in them that look like they might have been used as a sort of cosmetic, even.
So once again, Neanderthals turn out to be a lot brighter, a lot more advanced, if I know archaeologists hate using the word advanced, but that than we perhaps thought.
Well, if this genuinely is Neanderthal art, and we haven't yet proved it beyond all doubt, because conceivably it could have been made by modern humans a matter of a few hundred years after they first arrived in northern Spain. But if it does turn out to be Neanderthal, then it's showing that Neanderthals have the cognitive abilities rather similar to modern humans. So we've narrowed the gap in the difference between them.
But even modern humans, when they started turning up in Europe, they didn't have a culture of art before that, is that right?
Well, that's a very interesting question because, in fact, in Africa, we do find art objects around 70 to 100,000 years ago, which include little bits of engraved red ochre minerals. We find beads and bead necklaces, and we find engraved ostrich eggshells. But the earliest paintings in Africa are only around 25 to 27,000 years ago.
So a lot more recent than the ones here, for instance.
Absolutely. So it looks like the tradition of painting caves started in Europe. And that's a really interesting question to ask. Why should it be that humans should start painting caves in Europe and not in Africa when they'd been making art objects in Africa for the previous 50,000 years? And we think we've got an idea about why this is, and that is actually the presence of Neanderthals. And we find just after humans arrive in Europe, we find the first examples of musical instruments, of figurative sculpture. We may have found the first example of painting. And the difference between Africa and Europe at this time was the presence of Neanderthals. So it might have been that in order to compete for resources with Neanderthals, modern humans had to organise themselves differently socially, and art may have been one of these innovations that allowed them to create a group identity and therefore compete with Neanderthals.
Alistair Pike from the University of Bristol. And that was from our 3rd of July podcast, and there are pictures at Planet Earth Online. Even further back now to one of the great pivotal events in evolution. That moment when a creature emerged from the water and for the first time stepped onto land. It happened some 360 million years ago, but it wasn't a sudden event that we've perhaps been led to believe, nor it seems could the first animals actually walk. John Hutchinson from the Royal Veterinary College and Stephanie Pearce from the University of Cambridge have been investigating how these ancient creatures, known as tetrapods, moved about. John began our conversation by showing me some bones.
This is the pelvis or the hip bones and the femur or the thigh bone of a big, about a 4-meter Nile crocodile, which is superficially like one of these early tetrapods. It has the same basic bones, although the proportions are a bit different.
And to give you an idea of the scale, this bone is about, well, it's not that much smaller than my forearms. This is going to be an enormous crocodile, the sort of thing you wouldn't want to come across.
Yeah. It was a pretty big animal. The early tetrapods were only a meter or two long, so they were smaller. But anyway, the point of having these bones here is to show that we can use, to a certain degree, the bony anatomy of an animal to figure out what kinds of motions its joints would be capable of or not capable of. And that's really what we did with these early animals, as well as some living animals, including crocodiles, to compare them with. It was we built computer models that allowed us to wiggle the bony joints around, like I'm doing here with the hip of this crocodile, move it around in a computer and see how much mobility was possible in each joint. And that would constrain what kinds of postures or movements were possible in the extinct animal.
And then you were looking at these ancient fossils, Stephanie.
Yeah, so we applied the same procedure to our fossil animal, and when we looked at the mobility of the shoulder and the hip and the elbow and the knee, and we compared that to the modern animals that we were looking at, and we looked at modern animals in which we knew how they actually moved on land, so we could say, well, this animal has this much mobility in its hip, and we know that it uses this type of locomotion style on land. And we looked at our fossils, and we found that its limb joints actually weren't moving at all like that of living animals. And that could tell us that our fossil animal must have been doing something fundamentally different when it was moving on land.
Now, you've got an image, and you can see this on the Planet Earth Online website. You built this up from CT scans of this creature. Almost looks the head like a vicious fish, like a pike or something like that. The rib cage, yes, maybe something like an alligator or something like that. And then it's curious that whereas at the front limbs you could think, yeah, they look a little bit like legs, the back, they look more like flippers.
That's correct. The back limbs actually remind us of flippers in a seal. The lower portion of the limb is very, very flat, and there's no ankle joint, so it actually couldn't bend its foot and put its body weight on its hind legs. So these were giant flipper-like limbs that would have helped the animal while it was swimming, just like you can sort of envision for a seal.
So how would this have moved? It sort of drag itself along?
Yeah, it would have moved kind of like a mud skipper or a seal, so crutching itself along on its forelimbs, using the forelimbs together, not one at a time, left, right, but left and right, hauling itself along, dragging the tail behind it, probably to some degree dragging the hind limbs behind it. So it would have been somewhat awkward on land, certainly not a fast animal, and probably spending limited amounts of time moving around on land before going back to the water.
John Hutchinson and Stephanie Pearce in a room full of bones at the Royal Veterinary College in Hertfordshire. We'll finish with an extract from another of our audio diaries, recorded by Hannah Grist on the Isle of May, a rocky, treeless island near the mouth of the Firth of Forth in eastern Scotland. Depending on the time of year, the island is home to puffins, seals and shags. Hannah is studying these seabirds to see how the population varies over winter. We join her at dusk.
I'm currently nestled down a cliff on a small ledge, looking across at a cliff in the distance, where I can already see about 20 or 30 shags out there, and more are coming in all the time as the sun sets and they come off the sea to feed. So if you've never seen a shag, they're quite tall black seabirds, around about the size of a penguin, say, and most people don't tend to look at them because they're not very striking from a distance. But if you see them a bit closer, you'll see that they've got a brilliant iridescent green sheen across the feathers and really piercing green eyes. Now I am currently looking at them closely because I have a telescope with me here, which means that I can see individuals on the cliff opposite. And what I'm looking for are what we call colour rings. And so each of the birds that breeds on the Isle of May has had a large plastic ring attached, which has a 3-letter code inscribed on it. And if we can see the colour and the code, it means that we can identify them individually. Now that is easier said than done, although it doesn't sound too difficult to read 3 letters. Most of the birds will inevitably be standing on the wrong leg and tucking the other one up so you can't see it. Alternatively, they'll be walking across the cliffs, and they do have a tendency to fall over quite a lot because they're much better in water than land. And so trying to read 3 letters sideways from a distance on the move is definitely much more of a challenge than you would initially think. However, if we do manage to do that, it's fantastic because it means that we can see what's happening to an individual year round. So we can see what age it breeds, how many chicks it has, and where it's spending the winter. So we get a chance to look at anything that affects the individual, and it means that we get a much better idea of what's happening to the population as a whole. Now, it's really good for me as well to identify them on an individual level, because it means that I start to see the same individuals again and again, and you can get quite involved with watching them all the time. For example, at the moment, I'm looking through the scope and I can see red DEN, and I've been watching him all winter and last winter as well. And it means that I know he's sat on the same spot every time, and will always come back to it quite late on in the day and will turf off any juveniles that have dared to sit on the metre of rock that he prefers to be on. And at the moment, I can see that he's trying to find a mate, and he seems to be courting one particular female. And courting for shags means they're preening each other's necks and shouting at each other a lot. And they tend to curl their necks round each other and put their heads together, so it's kind of a equivalent of a shag hug. Now, I know a lot of people think I'm absolutely crazy when I say I spend my time out on Scottish cliffs in the winter. And I would occasionally agree with them. But really, I mean, my commute in the mornings is a 10-minute walk between seals and rabbits with no cars or people or other noise. And I get to sit here and I get to watch the sunset over the sea. I mean, my job basically is to sit here and watch wildlife all day, and who wouldn't want to do that?
Indeed, although making podcasts is pretty good as well. Hannah Grist on the Isle of May, and that is the Planet Earth podcast for another year, featuring science funded by the Natural Environment Research Council. Don't forget you'll find the interviews in full at Planet Earth Online. We'll be back in 2013. I'm Richard Hollingham. Thanks very much for listening.